All right. Good morning, everybody. I'm Steve. Thank you so much for coming to my talk. This is great to see so many people here. Today, I have a demo for you, and it looks like this. Oh, that's a tab. That's not refreshing the page. This says, "Hello, WASM." It's sort of a little small on this particular monitor. This simple alert box has a surprising amount of technology behind it. And what we're going to do today is kind of do a deep dive into exactly how this works. You may have seen some of this tooling before, but I'm kind of going to trace through the execution of how all of this actually happens through the different layers of the stack. Yeah, so that's kind of the point of this talk. So Rust and WebAssembly is fundamentally how this works. I am on the Rust core team. I work on the documentation for Rust, so that's why I love the Rust stuff. I technically am part of the WebAssembly community group, but honestly I signed up and haven't done any actual work, so it's like kind of like a title that doesn't really mean anything at the moment. I work at Mozilla, where many of my colleagues actually do real work on WebAssembly. I'm just a really big enthusiast for WebAssembly. And so I'm assuming you didn't show up to this talk not knowing nothing about WebAssembly, but if you only know a little bit about it, that's also okay. It's a pretty new technology. It's been about a year since it's been shipping in all of the evergreen browsers. And basically, WebAssembly is a technology that lets you run non-JavaScript code on the web, and specifically on the client side, but also I saw a tweet the other day that said something like, you know how AJAX stands for asynchronous JavaScript and XML, but like no one uses it with XML? It's kind of the same thing with WebAssembly, where the web is technically in the name, but it's actually a little broader than that. However, this is not a general WebAssembly talk, so I will not get into the like non-web browser aspects of WebAssembly. But just so you know, there's like a lot of interesting stuff about it that goes beyond even web browsers. This alert box was generated by Rust code that's actually like running in your browser. And so there's a lot of steps to make that happen, and this is a surprising number of steps. So we're going to go over first compiling Rust to WebAssembly itself, and then we actually put that WebAssembly into an NPM package. And I'll talk more about why that's important in a bit. Then we're going to set up a project with Webpack. Actually, I have one set up already. I'll explain to you a little project set up with Webpack. And then this web page loads some JavaScript that then loads the WebAssembly, and it calls into the WebAssembly to say, you know, hey, make this greeting, and then the WebAssembly calls back into JavaScript to actually do the alert box, and the alert happens. So we kind of have this like multiple layers of JavaScript, WebAssembly, WebAssembly to JavaScript, and all that shenanigans. And then we'll also talk a little bit more about WebAssembly, and depending on how much time we have, we're going to talk about the actual binary format that WebAssembly comes in and some of the nitty-gritty about that, and also the text format that accompanies it, and a little bit about when it might be appropriate for you to use WebAssembly today in your application, and why Rust is great for WebAssembly. Sean Grove is giving a talk in this room afterwards, like literally the next talk. If you like this topic, stick around, and he's going to be doing a much better job of 3 and 4, so I'm not going to really go into that in detail, because that's his talk, not mine. We didn't realize at first that we were like next to each other, so that's kind of fun. Okay, so Rust. Rust is a programming language that was originally sponsored by, and I mean still sponsored by, but like not in control of, Mozilla, my employer. And Rust has historically described itself as a systems programming language. But we've seen a lot of interest from people that are not traditionally systems programmers, and part of the reason is because systems programming is kind of a totally meaningless, useful term that everyone is confused about what it means. So what I like to say is that Rust is a programming language that lets you move anywhere up and down the stack. So, you know, this is an alert in a web page. My hobby project in Rust is an operating system. Like, it lets you go the whole way down to the whole way up and do all those kinds of things. So I have these two directories, and they're called backend and front end, which is kind of a little bit of a misnomer, honestly, because the front end is the website that's like running, so that's technically on a server, so it's kind of back end, but it's serving the HTML, whatever, it's fine. So the back end has the Rust code, and the front end has your like HTML, JavaScript, no CSS, if you can tell that I'm like a back-end programmer mostly. This is not the prettiest web page. It's so it doesn't distract you very much, but it's actually because CSS is impossible for me, and I really respect the people who do it because it's really good. Okay, so maybe this is actually a better way to do it. So here we have this Rust project. There's a whole bunch of shenanigans here that doesn't really matter too much, but the most important stuff is the src directory is where our source code goes, and the pkg directory is where our npm package is actually going to be compiled. We have a whole bunch of configuration files. Rust actually sets this all up for you. So earlier, we provide this like template you can use. So I actually typed cargo generate and then passed a URL to it, and it actually generated the start of this template for me, so that I didn't have to like create all these files. And obviously not all of them are absolutely necessary. For example, there's a .travis.yaml in there you might see. This is not even like on GitHub really, so it's not part of Travis, but we generate one that actually like does the right things for you and all that kind of stuff. But let's look at the actual source code. So here is the Rust code that actually generates. Oh man, Visual Studio Code really wants me to install all this stuff. Here's the code that actually generates this alert. So if you haven't seen Rust syntax before, it's sort of a curly braces and semicolons language. We wanted to stick with the sort of C-like semantics, but there's also some stuff that's a little different as well, some inspiration from functional programming languages. So the first two lines I'm not going to talk about right now, but lines 4 through 9. So line 5 describes a function with the fn keyword, and it's a public function because we're going to be calling it from outside of our library. So pub fn. I like to joke that we learned from JavaScript, so we don't have to type function out every single time. We just type fn because typing function every time is a long thing. Rust has some short keywords, but some long keywords. Originally, a really, really long time ago, Rust had a rule where no keyword could be longer than 5 characters, which made for really awkward situations like continue became cont, because like that doesn't fit. And so eventually we realized that was kind of stupid and relaxed most of them, but there's still a little bit of like the most common ones where it's like pub fn to declare functions. And we're calling this function greet. You're going to see that a little bit later in our JavaScript code. But here, this function has 2 lines in it. The first one declares a variable called window, and it calls a function called window to set that up. And then these 2 expect method calls, basically, Rust is extremely strongly statically typed, and it really, really, really wants you to do things like handle errors. But I'm using expect to say, hey, if this function errors, just like blow up. Like, I don't care. Is basically what those things mean. And unlike JavaScript, I actually have to handle those errors, and so it's going to make me do something, but it can't make me not just blow up. So I'm not doing real error handling here, because that's kind of not really the point of the demo. And also, if we can't get access to the window, there's not really a whole lot we can do other than just throw up our hands in disgust anyway. So it's kind of actually not that terrible of an error handling strategy, especially for a demo. But this call to window is actually fetching the context of the browser window itself, like window in JavaScript. And then on line 8, we call window.alert with message, hello WASM, and expect again. So this is actually the alert function in JavaScript. But Rust does not have function overloading, and it turns out that, did you know you can actually call alert with nothing in it, and it just pops up in box with like nothing in it? I didn't until I started writing this demo. And so we have to have alert and then alert with message to like pass the arguments, because without function overloading, you need a different name for each function with different arities. So all this window stuff and alert from message comes from line 2. So there is a package that we've built called WebSys, and sys is this like convention in Rust to sort of mean the low-level bindings to some other form of a system. And so these couple little lines here about WebSys and window are actually pretty in-depth themselves. So there's this specification called WebIDL, which is an interface definition language that all of the browser vendors use to implement the web platform. You can kind of think of it as like a specification for the specification, but in code that you can actually run. So the W3C and the WG and all those standards bodies, they write English to standardize the stuff, but then we kind of turn this into code that things can actually read. So what we did was we took that code out of Firefox, and there's a tool that we run on it to generate WebAssembly bindings for Rust for everything on the web platform. And so there's these two packages, WebSys and JSSys. JSSys is for the entire JavaScript language, everything that comes with JavaScript natively, and WebSys is everything that comes in your web browser. So we actually have full bindings to everything today, and I'm using those kind of auto-generated bindings to make this work. You can do it by hand, and it's actually even a little bit nicer looking, because then you can just call alert instead of alert with message, because you're just binding to the regular function. But I wanted to show you the full sort of production stack in some sense. But this is really cool because it means that we're automatically in sync with what browsers are actually doing. And when they add new features to the platform, we can regenerate those bindings and push a new version of the package, and then you get full access to all that stuff. So this is one definitely really interesting area of tooling that I'm only using a little tiny bit of it. Because it's auto-generated and this, this message, or this situation with alert with message, it can get a little bit dicey. I've seen there's one or two bindings where, when you have a particular function on the web platform that takes 4 arguments and 3 of them are optional, and then you end up with this really long call X with Y and Z and A and B or whatever. So it's not always perfect, but at least maps directly to the things that you would actually call. And so lastly, lines 1 and 4. This is where a lot of the kind of magic happens. So there's this project called WASM bindgen, and bindgen is short for bindings generation. There's a bunch of different projects in Rust with the name bindgen. They do various things. This one specifically lets you bind Rust code to WebAssembly. So we're bringing a bunch of the stuff into scope with line 1 from that package, and then on line 4, when we annotate this function with WASM bindgen, we're saying, hey, I am planning on exposing this Rust function to WebAssembly. And there's also a way to annotate the function when you say, I plan on calling this function from WebAssembly, but that is inside of the WebSys package. So you basically use the same annotation with some slightly different Rust syntax. But so the combination of this annotation WASM bindgen and the pub on greet means that this is going to be our public API that we're exposing to the world in WebAssembly. So we have that. The next step is to actually compile. Well, I should show you one more thing about this before we compile, actually. Rust has this tool called Cargo, and it's kind of like the NPM for Rust, but the good parts of NPM, not necessarily all the parts of NPM. We took a lot of inspiration from Ruby gems and NPM and kind of took the best of both of them and made this package manager / build tool for Rust. So here's kind of what that file looks like. You can ignore basically all of the shenanigans. This particular annotation says that we're planning on, since this is a deep dive, I'll actually tell you what this means. This crate type, so Rust packages are called crates, and basically this is saying that we want to build a C dynamic library, which means no Rust-specific information, but also a Rust library, which includes some Rust-specific information. So we can technically use this from both Rust and WebAssembly, although with no context to the window in Rust, that's not super likely going to work. But we can specify the different dependencies that we have. And so here, we're depending on version 0.2 of WASM bindgen. And this is actually a semver range. So this will actually add any specific version in the 0.2 series of WASM bindgen. And there's this lock file that whenever you actually do the build, it will pin that particular version down. And then for WebSys, we need a little bit of configuration. So because you probably don't want to include the entire web platform in the binary of every single WebAssembly binary that you build, WebSys and JSSys have these feature flags that let you toggle, this is the exact features of the platform that I'm using. So here I'm only including support for Windows stuff, since we're only using Windows stuff. And then there's some test shenanigans. And then finally, we're going to tell Rust to optimize for size. binary size is really important to web developers, right? Because the smaller that you can make your assets, the faster that they download and the faster they load. And kind of one of the points of WebAssembly is to be smaller and faster than JavaScript anyway. So by default, binaries can be sort of medium-sized, but if we tweak a bunch of different things, and I've only done one of these tweaks here, which is specifically tell Rust, hey, I would like you to compile to optimize for size rather than necessarily to optimize for speed, we will get a smaller binary. And this is one of the advantages that Rust has, is that we can produce very small binaries because we do not have a runtime with a garbage collector or anything like that. So the smallest binary that I've been able to get Rust to produce is 110 bytes. A simple function that just adds 1 to a number and returns it will give you like roughly 100 bytes, which is pretty good given that writing that by hand, like in the actual WebAssembly code by hand, would be about 50 bytes. So there's like 50 bytes of overhead, but it's not that big of a deal. And so you're able to get pretty small actual binaries with Rust. Okay, so in order to actually compile this, what we do is we run rasm pack build. And so wasm-pack is this tool that wraps cargo, and it's compiling all this stuff here. You can sort of see the first thing it does is it makes sure that you have the right version of Rust installed and that you have the configuration set up properly. So if I was missing that cdylib attribute, for example, it would fail and be like, hey, you actually need to set up this thing correctly. And if you had the wrong version of Rust installed because previous versions of Rust did not necessarily have support for WebAssembly, so it checks to make sure that you have that set up correctly as well. And then it will actually add support for WebAssembly to your Rust installation if you do not install that support. And then it will actually compile the shenanigans. And you can see there's sort of a lot of dependencies. As I said, we did take some inspiration from NPM. So the Rust ecosystem tends to be a lot of relatively small packages built on top of each other. And then I actually built this morning, so I'm not sure why it's rebuilding, but you can see compiled languages, you have to wait on the compiler sometimes, and the Rust compiler is not the fastest for various reasons, but it should almost be done, maybe. Come on, computer. All right, anyway, this is pre-compiled, and I'm not going to make you sit and wait here. But the point is that we get this pkg directory, and this actually is what wasm pack spits out. And so this ends up becoming our npm package. Now, why are we generating an npm package? Well, a lot of what you've heard about WebAssembly is kind of like write your entire web front end in WebAssembly. And that's definitely something that you can do, although there's some reasons why that's not super optimal at the moment. But let's put a pin in that for now. The strategy that the Rust project is taking with WebAssembly is that we fundamentally believe that JavaScript is a good programming language that people actually like to use. And so what we want to do is give JavaScript developers the ability to augment their JavaScript with some WebAssembly. So you don't necessarily need to rewrite your entire front end in WebAssembly. You can take the hot path and replace that with just a tiny little bit of like a sprinkling of WebAssembly. And so also, given that WebAssembly now runs in Node, there's also an opportunity with JavaScript on the server to also be enhanced by WebAssembly stuff. And so our sort of like idea and what we believe is going to be true with WebAssembly in the future is that JavaScript developers are going to start using WebAssembly without even realizing it, because you're going to be depending on packages that are implemented in WebAssembly, and you just don't even have to think or care about that. It turns out that NPM does not validate what you put inside of an NPM package. You can put literally anything inside an NPM package. Visual Studio Code, right here, if I type Control F, like if I have this file open and I search for something, or it's not Control F because I have the Vim bindings installed, but like if I do a search find, this is actually powered by Rust. Visual Studio Code uses a Rust project called ripgrep, which rips through it greps super fast because it's ripping through your results. But that's because Visual Studio Code is written in JavaScript, it's built as NPM packages. So Microsoft built an NPM package with pre-built binaries of like actual Rust code inside of it, and there's literally no JavaScript in those packages at all. It's binary code that's from like actual Rust binary. So not WebAssembly, but like actual machine code. So what you can do is you can create an NPM package where it contains the pre-compiled WebAssembly, and then you don't need a Rust compiler or any other of the tools installed because it's already pre-set up for you. So here's the contents of this package. You can see that there is, first of all, a README. We automatically take the README for your Rust project and copy it over to your NPM README so that when you upload it on npm.js, you can see that stuff on their website. And then this package.json, because all things need a package.json. That's what makes an NPM package. And then finally, there's this backend bg.wasm and backend.js. That's the actual code, so the WebAssembly code that was compiled from the Rust code. And then you need a little bit of JavaScript to wrap that for reasons I'll talk about in 1 second. The last thing, though, is this backend.d.ts. We can generate, because we are also a typed language, we can generate really good TypeScript bindings for your project automatically. And so when you're using this WebAssembly package through NPM, you will actually get full things like auto-completion in things like Visual Studio Code because we're using the TypeScript bindings. And this is a really popular thing even with JavaScript packages, but you just kind of get that automatically for free because Rust has types, so it works out. Now, this JavaScript file and the WASM file, the way that WebAssembly works is you actually use JavaScript to load up those files, and so you need a little teeny bit of JavaScript. So this is generated by WASM bindgen for you, and additionally, WebAssembly does not support anything other than numbers, basically. So if you want to pass a string from Rust to JavaScript or from JavaScript to Rust, normally you're on your own to write that by hand. But WASM bindgen knows how to take arbitrary JavaScript objects and almost arbitrary Rust stuff and do the marshalling across the boundary for you, and that's largely in this file. So this is all compiler-generated shenanigans. So you can see that our package imports our WebAssembly, and then it exports a function called greet that calls greet from our WebAssembly code. And then here is all of this shenanigans that is often needed if you're doing all sorts of these other things. So like, certain utility functions and blah, 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 and there's some garbage here. So we have like 100 lines of shenanigans, and this is all what makes that stuff sort of work. We don't use a whole ton of it in this particular instance, but as you do more complicated things, you'll get more shenanigans here. And also things like JavaScript strings are UCS2 sort of, and Rust strings are UTF-8. So when you pass a string across the boundary, you have to do the string encoding to get the right encoding and all that kind of stuff. Okay, so we now have a NPM package with some Rust compiled WebAssembly code in it. How do we actually use that in a real project? Well, let's go to the front end directory. So here I have a simple project set up with Webpack, and I'm sure the people that use Webpack in the room are like, simple Webpack project is kind of a contradiction in terms. I know Webpack is great, but real production tools are complicated. That's just how it goes. But we have a 15-line Webpack config set up here. This is really just the sort of the absolute basics. We have this particular plugin, and then we say, okay, the entry point is this bootstrap.js file, and we're going to copy it over in development mode. There's not a whole super ton of this going on here. This front end is also, I can get this started by using an NPM package. So there's a create, just like create React app exists, if you all have used that in the past, there's a create WASM app project that you can use to sort of generate an initial hello world project, and that's what I use to make this demo. So we have this Webpack config, and then all right, so here is our extremely basic HTML file with this going over the demo and the tiny detail that you saw earlier. This has a link to a bootstrap.js file, and then in that bootstrap.js file, all that does is it loads up an index.js file. The reason this happens is for reasons. The WebAssembly stuff should be loaded asynchronously. So the template that I'm using generates this import statement and then catch to load this JavaScript function asynchronously. And there's some reasons why that's cool. I'm not actually 100% sure why it's necessary, like this comment says. But one really interesting thing is that WebAssembly supports what's called streaming compilation. So that means, at least in Firefox, Firefox can compile the WebAssembly faster than your browser can actually download it. Like it can start compiling it as soon as it gets the bytes off the wire. It can actually keep up as it downloads the thing. So you want to do this all async in order to get the maximum speed, because that's what we all are using WebAssembly for in the first place. But our index.js, extremely complicated. Import star as WASM from backend. So if you remember, we called our Rust project backend. So this is now using that npm package, and then we call the greet function on that WebAssembly. So you can imagine, like when I say you're using npm packages and you don't realize they're implemented in JavaScript, from a front-end perspective, this is the code that you write to use that WebAssembly. It looks and feels no different than any other JavaScript code. Other than maybe having like very simple name here, greet, like arbitrary function. But like, this is kind of the cool thing, is we can hide away all these messy implementation details about how it's like actually implemented, and you just kind of use it. And so where does it get that backend from? Well, we have our package.json, and here, newer versions of NPM let you depend on a file path directly. So you can do that, or if you want to mess around with npm link, you can also mess around with npm link, but I always screw up npm link, so I try not to use it. And so here I'm just saying we have a dev dependency on backend, which comes from this particular file path, and we're pointing towards where that was. So you can upload these packages to the npm.js registry. npm loves you adding more packages to the registry, and so you can also do that, of course, and use it that way. But you can also do things locally if you'd prefer. And then we have a couple other small dependencies on the Webpack stuff. And so that's really it in terms of this code and how the code works. And then, I just have a terminal over here running. You can also see that I have a start script that runs Webpack dev server, and that's what's running in this terminal, and that's what's running whenever you load up this web page. So that's kind of the whole sequence of things with all the little bits and the pieces that we generate for you, and how all that stuff kind of works. So we have our Rust project in Cargo, compile it into an npm package, and then we depend on it with Webpack, and it all just kind of works out. So yeah, that's kind of those particular details. However, I also would like to talk a little bit more about the details of WebAssembly itself, because we sort of said okay, Rust compiles to WebAssembly and we put that WebAssembly in a package, but we didn't really talk about what that actually was. So WebAssembly has two different formats, and as an assembly, you can get all this stuff, which is cool. So one of the reasons why WebAssembly is sort of an advantage over generating JavaScript and using that, there's a lot of compiled to JavaScript languages, is that it is a binary format. And that means that it is very tiny and compact. So this is a particular web page called the WebAssembly Code Explorer. And what I've done is I uploaded the file that we generated out of Rust and WebAssembly. So I uploaded it here, and then this actually shows you the actual assembly. I mean, by actual assembly, I mean the binary code that is in the WebAssembly file. And then because most humans don't want to be reading this, there's also a text format that you can generate out of WebAssembly losslessly from the binary. So view source is a really important part of the web, even though you could argue that our packed up and minified and obscured JavaScript is barely useful with read source anyway. It's really important to be able to get text out of whatever thing you're running in your browser. And so one of the design goals of WebAssembly was to have a text format. And so if you see there's a whole lot of parentheses, it turns out Lisp actually did win in the end. And you can read this code. However, debugging this is really only one step up from this. And so one of the things that's being worked on in WebAssembly land right now is not technically source maps, because nobody likes source maps, even the people who came up with the idea of source maps, but the general concept of there's a file maps your original source code into whatever this stuff is, so that you can do that debugging wise. And so in Firefox, that sort of kind of works sometimes. already, and everyone is kind of working on it. But sort of the idea is that whenever you are debugging your WebAssembly code, you should ideally be able to see your Rust or whatever you're compiling into WebAssembly inside of your inspector. But even if you don't have that, you at least get this. What I really like about this tool is it lets you click on the text on the right, and it actually shows you the specific bytes in the binary on the left. And this is really interesting, especially I actually wrote a binary parser for WebAssembly to learn the format a little bit better. The WebAssembly spec is really awesome, by the way. If you get the chance, you should read it. If you're the kind of nerd who likes to read specs, I am that kind of nerd. I acknowledge not everyone is, but it's actually really well written and really helps you understand what WebAssembly is and how it works and what it does. But anyway, the point is that we have all this different stuff over here, and then these color codes mean different things. So I'm not going to talk too much about all of this shenanigans because it is literally binary code. But on the right here, and I think, no, I cannot actually slide that over, so whatever, it's not that important. If we look at the actual text format of WebAssembly itself, so we start off with this module declaration. I know this is a little bit small. I'm sorry. I don't think I can make it too much bigger without totally ruining this part of things. So we start off with this module declaration, and then there's 7 different kind of sections that can appear in a WebAssembly module. And so the first one that appears is these type declarations. So WebAssembly is fully typed. And actually all the function bodies are also typed, which is really cool. So you can do static analysis on the execution of the WebAssembly without ever actually running it, which is really cool for security reasons. But we have all these different type declarations, and the reason they're separate from the functions, so this says, I have a type declaration, we're calling it type 0, and it's a function that returns a 32-bit number and has no parameters. And that is totally set up separately from the body of the definition because you may have many functions that have the same type signature, and we want to make this binary as small as possible, so we only encode one type for every unique type of function that exists. So here we have 14 different types of functions, but we're actually defining somewhere in the area of 26 internal functions because they reuse the same type declarations. So that's one example of how WebAssembly kind of makes these files smaller. And then we have an import section. So the import section is saying these are the functions that I expect to get when the project actually imports me. So if you notice in the backend code, when we load up the WebAssembly function, or when we load up the WASM from JavaScript, what we end up doing is, or actually I guess this is the, oh yeah, this is the right one. There's all these functions in here that we also export. So instance of window, for example, is exported. And so you can see there is a instance of window is over here. So these are all the functions that we sort of expect that our JavaScript file that's loading up our WebAssembly is going to provide for us. And so this is kind of how you can make WebAssembly call arbitrary JavaScript functions, is when you instantiate the WebAssembly module, you pass these JavaScript functions in, but you don't need to do any of this by hand when you're using this tooling, but at the low level, that's how this actually works. And so these import statements are all the things that are able to be called from JavaScript. And so this is also really cool for security because we can look at the WebAssembly module and see guaranteed exactly what it's going to call from our outside environment, so we can know that we're not making calls into our password manager or whatever, all that kind of shenanigans. There's this table and memory section I'm not really going to talk about too much because I do not have a million years up here. This talk is almost over. There's a global section that lets you sort of define global variables, and then you can export things as well as import things. So WASM expects you to export some memory. So WebAssembly has this concept called linear memory, which is kind of like what your hardware lies to you and says that you have infinite RAM that's all in order when you actually only have so much. WebAssembly has the same sort of model, and so we can expose memory to JavaScript and manipulate it from JavaScript and also from within WebAssembly. And then here, finally, this line, these little bytes, 05677265657400F, this is the thing that actually exports that greet function to the outside world. So when we're calling from JavaScript, we're calling into this particular exported function. So just like we're importing functions from JavaScript, we export functions to JavaScript, and we're able to call them. And then finally, here is what like an actual function body looks like. So this is the last section we're gonna go over. As you can see, it's an assembly language. i32.store, i32.load, i32.const1. WebAssembly is what's called a stack machine, and so each of these different instructions does something different. So get local var0 will actually get the first parameter off of the thing, and then we load up a 32-bit number, and then we load up a 16, and then we do all these other things. So this is very sort of like simple and low level and does all these things, and that also means that there is a bunch of it. So yeah. Just like real assembly, at first this kind of seems like impossible, and you're like, whoever wants to read this? And then if you get really into it at some point, you're like, I actually understand what this is doing. But again, obviously, when you're debugging your front end, you don't want to be reading this garbage. So that's why the debugging and source map stuff is like really actually important, and why it's something that we're deeply working on. Okay, so I only have about 5 more minutes. The last thing I want to tell you about the text. Nerds. So the WebAssembly function is .wasm, but the WebAssembly text version, the file extension is .wat, WebAssembly text. So yeah, that's a thing now. I don't know who picked that exactly, and if I don't know if it's because of Gary Bernhardt's talk called WAT, if you've ever seen that, but it's funny regardless. So yeah, so you have the WebAssembly WASM file and the WAT file, and you can actually, there's tools to convert back and forth between them. So you have like WASM to WAT and WAT to WASM are the tools that like will go back and forth between the two. So that's also kind of like a funny particular thing. Okay, so lastly, let's really extremely briefly go over these points 3 and 4, and then you should definitely stick around to see Sean's talk next. But when it's appropriate to use WebAssembly today. So WebAssembly is currently supported in all evergreen browsers, and by that I mean Chrome and Firefox and Edge Internet Explorer. The only thing that's not supporting it is non-Edge IE, so like IE 9 and those kinds of things. And so really, you can only really truly use WebAssembly stuff if you're willing to sort of get rid of those older Internet Explorer users, which may or may not matter to you depending on your industry. If you need to support those older Internet Explorer browsers, there is actually some ways that you can compile the WebAssembly binary to JavaScript and then sort of run it in an interpreter, but like you're using WebAssembly for speed in the first place, so that's not as fast, so that may not actually be a practical application. So that's one area where you can't use WebAssembly. However, like it works on phones and in mobile browsers as well. So there's actually pretty broad support because all that landed about a year ago, and there's been a lot of progress that's being made. Secondly, as I said, you can rewrite your entire front end in WebAssembly if you'd like, and there are projects even in Rust to do those things. If you happen to check out Hacker News in the last couple days, Bodil Stock released like JSX for Rust, which is kind of really cool and intense. You can sort of write HTML templates, and it's actually all type checked even, so it can actually say like, hey, that's not a property on that particular tag that you have, which is really cool. I think the bigger area is augmenting your JavaScript. So, for example, Dropbox put out a little demo where they have a new compression algorithm, and they wrote it in Rust and compiled it to WebAssembly. And I don't think they're actually doing it in production yet, but the idea is that Dropbox's core business is storing your files on hard drive somewhere. And so that means you're uploading files to them, oftentimes through a web browser. And so the idea is that you could compress the file in the client before you send it over to the server, which saves on things like transmission costs and all that other kind of shenanigans. And so they do that with WebAssembly. WebAssembly is also a much more sane option than JavaScript for crypto in the browser because we have actual integers as opposed to floating point numbers. I always end up talking about integers when I talk about WebAssembly because integers are awesome, but because I'm used to working in lower level languages where integers are much more reasonable than floating point numbers. So there's some times where you're doing like particular kinds of number crunching, and that sort of stuff can be more useful to do in WebAssembly and kind of like augment it in your app. And so I think those kinds of like little small use cases are where we're going to see stuff. It's definitely really early days though, and other than some really like cool tech demos, I don't have a lot of great production like usage stories for you yet. This is cutting edge technology, and so you should only really be using it if you're willing to be using cutting edge technology. And then maybe in a couple years time, I'll be talking about whatever your thing it is the like the go-to example of production WebAssembly. But you definitely should know that it is not like a thing that's already conquered the world and is already here. Like it's mostly like toys and experiments at this point. And finally, for why Rust is a great fit, in my last minute that I have here, Rust, because it has no runtime and no garbage collection, makes it a really great fit for WebAssembly because you're able to get these really, really tiny binaries, which really matters. But additionally, the Rust team cares about making Rust awesome for WebAssembly. So all of this tooling that I've shown you like takes time and effort by humans to actually produce, and we are heavily investing in actually making those tools and making them really great to use. And so we also have one of the best, if I like brag about my team a little bit, we have one of the best like developer experiences for writing WebAssembly code. There's a lot of little tiny demos, but things add up over time. So like being able to generate that NPM package automatically is like a really big deal. Being able to bind to all of JavaScript and all of the browser's APIs. I'm not actually sure that any other language has like complete full bindings in that way yet. And so we are like really, really investing in this heavily because we want to make it super awesome to make it a really great fit. Tons of other reasons, but you should stick around for the next talk. That is all I have for you this morning. I've been Steve. Thank you so much.